Hello students, let us continue our discussion on the first law of thermodynamics, where we are trying to quantify the relationship between internal energy, heat and work. I have already told you that if there is a finite change in state in a closed system, then delta U, that is the change in internal energy, is related to a sum of the heat and work that is done either on the system or by the system during the change in state. And for an infinitesimal change in state, there is an infinitesimal amount of change in the internal energy, which I represent by the exact differential du. Then du would be equal to dq plus dw. And I've also talked to you about several different processes that are usually used to carry out this change in state. And apart from the last set of processes, I have described to you how to represent the other processes like isothermal, isobaric, isochoric, adiabatic, cyclic processes. Now let me tell you a little bit about what are reversible and irreversible processes. Okay, so when I talk about an irreversible process, it is a process that occurs rapidly in a single step. Then, as a result of the different ways in which we are carrying out these experiments, there will be two entirely different situations when I have a reversible process and compare it to what happens if I have an irreversible process. During a reversible process, simply because I'm doing it very slowly and I am allowing only an infinitesimal change to happen at each stage of the change in state, the system is allowed to remain in equilibrium with its surrounding at each of the intermediate infinitesimal stages. Okay, but that doesn't happen when I have an irreversible process. So the system, as it passes from the initial state to the final state, it does not remain in equilibrium with the surrounding as it passes from the initial to the final state in an irreversible process. As a consequence of the way we carry out the reversible processes, the backward changes of the thermodynamic quantities at every stage is the same as the forward direction but opposite in sign. But of course, in irreversible processes, forward and backward changes of the thermodynamic quantities are unequal. So let me take an example and try and see how we experimentally realize these two processes. I will start with the same system, same initial state, where a gas is contained within a cylinder and its volume is fixed by putting a set of stops on the bottom of the cylinder. There is a second set of stops here, but in the initial state, I am not using them. Now, if I want to carry out the reversible change in state, what I will do is I will very slowly decrease the weight that is holding the piston down, and I will withdraw the steps, these stops very slowly through very small amounts. So what will happen? Then through a very large number of steps, I will slowly change this initial volume of the gas to a final volume of the gas where the upper set of stops will ensure where the piston comes to rest. So in the final state, this is the volume occupied by the gas. Now, if I want to represent this change in state in a PV indicator diagram, and if I carry out this change at an isothermal condition, then I will find that this change will be represented as something like a system going from here to here, where the volume increases and the pressure decreases. Now, if I want, and all the intermediate points will be present here on the PV indicator diagram. But if I carried it out in a one single swift rapid step, so I rapidly withdraw the stops and rapidly withdraw this external force holding the piston here. In one step, the gas will expand and the piston will get arrested by these upper set of stops. So this is an irreversible process. And in this process, it is only the initial and the final state which are equilibrium states. In between, the system is thrown out of equilibrium. And therefore, in the PV indicator diagram, I will have only the initial and the final states, but not the intermediate states. That is because a PV indicator diagram usually plots only those values of P and V under this given isothermal condition when the system is in equilibrium. Now, moving forward, therefore, I would say that here I have highlighted the fact that the reversible process takes the system from the initial state through a final state through an infinite number of steps. And while it passes through these very small intermediate steps, the system retains virtual thermodynamic equilibrium with its surrounding. But an irreversible process is where there is only one rapid single step taking the system from the initial state to the final state, and therefore there is no question of allowing the system to equilibrate with its surrounding in the intermediate times. Now, this brings us also to the question of how exactly am I going to supply heat to the system or take heat away from the system. So let me just remind you some of the concepts that you already know. So heat is transferred between a system and surrounding by virtue of a temperature difference only. And since it appears during the change in state and it appears across the wall, therefore heat is not a state function. And therefore, it depends on the path that the system has taken in going from the initial state to the final state, during which the heat is exchanged between the system and the surrounding. And heat can be transferred reversibly or irreversibly. Then a reversible transfer of heat requires the temperature difference between the system and its surroundings to be infinitesimally small. In that case, what you will do is, in order to go from the initial state to the final state, you will supply infinitesimal amount of heat from the system to the surrounding or vice versa. Now, coming back to the concept of work, in this lecture, we are going to talk about pressure volume work only. Or in other words, we are going to think of work that is being done by the expansion or compression of the gas. The typical way to estimate how much work is done during a change in state is shown in this figure. So what you have here, an external pressure P external holding this piston of area A, and by applying this pressure, I am allowing a displacement dz as shown in this picture. Now, if A is the area of the piston and if dz is the displacement of the piston because of the external pressure, as the gas pushes this piston up against this external pressure, what is going to be the change in volume for the gas? That is going to be dV, which is A into dz. So that is the volume change for the gas as it expands against the external pressure P external. Now I am going to calculate the amount of work that is done as the gas expands through this infinitesimal change in volume dV. Now the work required to move an object a distance dz against an opposing force F is W, that is equal to minus F dz. Now what is F here? I am replacing F here by P external into A, that is the pressure working on the area A gives you the force acting on the system. Now if P external, I just leave it as such and recombine these two terms, and what is the combination of these two terms? That is nothing but dV. And therefore, I find that the most general definition of work is W equal to minus of integral P external into dV as we go from the initial state to the final state. Now, by definition of a reversible process, as we move from the initial state to the final state, I am changing the external pressure infinitesimally so that the system pressure, the pressure of the gas, is always equal to P external. And therefore, only for reversible processes, I can replace P external by P, that is the pressure of the gas. And therefore, if I know either the P external and how much is the change of the volume during the change in state, I can estimate what the amount of work done is. Or else, if I have a reversible process, in that case, if I can express P as a function of volume, in that case, I can evaluate this particular integral, and that will also give me a route to calculating what the amount of work be involved as I pass from the initial state to the final state. So let us also mention that the pressure volume work is not the only type of work that is known, but in this course we will focus our attention to pressure volume work only. Now let us again consider expansion against constant pressure, and here we have the following. If I am carrying out an expansion against a constant final pressure, so that is the kind of situation that has been shown in this figure. So here the gas is expanding against a constant pressure P external. Now can I find out what W is under such condition? So as you see that since P external is a constant value, I can take it out of the integration, and then I can do the integration and say that the result is minus P external into final volume minus initial volume, which is nothing but minus P external into delta V. And here is a graphical representation of the magnitude of this work done. So my initial, in this case, my initial volume is this, my final volume is this, and work has been done against this constant external pressure, and the amount of work is minus P external into delta V. So what is this magnitude in this particular plot? P external into delta V is actually corresponding to the area that has been shaded in green here. And therefore, if you know how much volume has changed and what is the constant pressure, then I can find out the amount of work done here. Now, if I am expanding against a constant final pressure, in that case, I can replace this P external by the final pressure, which I designate as P final. Once again, I will be able to estimate the amount of work done in a process like this if I know the final constant pressure, if I know the initial volume and the final volume. Now, if I have another situation which I call the free expansion. So, what is a free expansion? A free expansion is the expansion of a gas against zero opposing force. So, as far as this equation is concerned, this would mean that P external is equal to 0. And if that is so, then I must be having W is equal to 0. That is because W is nothing but minus P external into delta V. So, basically, if a gas is expanding into vacuum, there is no opposing force, and in that case, I would say that it is a free expansion and the work done in this process is equal to 0. Now, these are all examples of what we call as irreversible processes. Okay, but now we can also think of reversible processes. So, let us go ahead and have a look at the difference in work in a reversible process. But before that, let me point out one more thing. When I have an expansion kind of work, in that case, what I can see is the following route. So, I have Vf greater than Vi. So, if Vf is greater than Vi, then if I go back and look at the expression for delta V, if delta V is Vf minus Vi, therefore, in an expansion, Vf greater than 0, which means delta V is greater than 0. And what is W? W is equal to minus P external into delta V, and therefore, W is less than 0. And this is therefore consistent with the fact that we are taking W to be a negative quantity when the work is being done by the system on the surrounding at the expense of its own internal energy. Now, if there is compression, in that case, Vf is less than Vi. Correspondingly, delta V is less than 0. Now, if delta V becomes negative, there is already another negative sign in front. Therefore, W will become greater than 0. Therefore, work is done on the system by the surrounding. And in this process, energy is being added to the system, and therefore, I would say that the internal energy will increase, and therefore, this definition is consistent with the sign convention that we have adopted so far. Now, let us take this specific example of pressure volume work being done by or on an ideal gas. So, once again, we will be using this definition that W is equal to minus P external into dV as I go from state 1 to state 2. But here, simply because my working system is an ideal gas, therefore, I will have this additional relationship that PV equal to nRT, where P is the pressure of the gas in a given state, V is the volume of the gas, N is the number of moles of the gas present, T is the temperature, and R is the universal gas constant. Now let us have a look at what is the work done by an isothermal expansion of an ideal gas. I would like to start first by looking at what is a reversible isothermal expansion. Now, as you understand that by definition, a reversible change will require the P external to be equal to the pressure of the gas at every stage. And now I'm going to use this in combination with the definition of work to find out the result. So I'm going to write that W is equal to minus 1 to 2 P dV. Now for an ideal gas, since I have an ideal gas, I can always write down the P as nRT by V into dV. Now you see the integrand is a function of volume, and therefore I can carry out this integration provided I know how temperature depends on volume. Now under the given condition, I have N constant, R constant, and since it is an isothermal process, therefore T is also constant. Therefore I can write that W is equal to minus nRT integral 1 to 2 dV by V. Clear? Now, in the initial state, the value of the volume is V1, and in the final state, the value of the volume is V2. And therefore, I can very easily write down that the result of my integration is nRT ln V2 by V1. I think this is very simple mathematics that all of you know about. So what is my observation here? My observation here is as follows. First, since W is dependent on ln V2 by V1, so if there is an expansion, V2 is greater than V1 and then W is less than 0. That is, work is being done by the system at the expense of its own internal energy. If V2 is less than V1, then W is greater than 0. So this way you can analyze this particular relationship that you have derived for a reversible isothermal expansion of an ideal gas. So let me conclude this lecture by saying that we have seen that the first law of thermodynamics has introduced us to the concept of internal energy, and the change in internal energy during a change in state is caused by either exchange of heat or work between the system and the surrounding. And we have seen this very simple example of how to estimate the amount of work that can be done on the system or by the system under reversible or irreversible change in state. So in the next lecture, we will be talking about not only the isothermal change in state, but the adiabatic change in state for an ideal gas and how to estimate the work done in such a condition. Thank you.